Hi, this is Jan Gray, and today I'm presenting the slides for the poster, Composable Custom Extensions and Custom Function Units for RISC-V, to be presented at the 2022 Spring RISC-V meeting in Paris. First, a bit of a backstory. This work began in 2019 with the formation of the RISC-V FPGA soft CPU SIG, whose charter is presented on the right. One of our goals was to propose extensions and platform profiles to enable interoperable RISC-V FPGA platforms and applications. We started a subcommittee to propose interop interfaces for composing customizable soft processors with custom function units. We felt that a thriving ecosystem of CFUs required a way to reuse and mix multiple accelerated library solutions together. That led to discussions and then a related spin-off called CFU Playground, whose work includes CFUs that accelerate TinyML inference workloads. Then yet more discussions, and now finally a draft proposed specification. So here's the poster, and now I'll discuss each section of the poster. RISC-V has both standard extensions and custom extensions. The standard extensions layer and compose well, but each extension must be of broad interest in general utility and non-proprietary, and each necessarily takes years to spec, drive consensus, and ratify. Conversely, custom extensions allow rapid development of in-house accelerators and accelerated libraries. Unfortunately, these solutions may not work well together when you bring them into one system. They may have conflicting instruction encodings, they may use different pipelining, signaling, different means of discovery, computation, state management, error handling, or versioning. These incompatible solution silos limit reuse and fragment the RISC-V ecosystem. Instead, let's build mix and match custom extensions that combine the agility of custom extensions with the guaranteed composability of standard extensions. Therefore, we have proposed hardware-software and hardware-hardware interop interfaces to enable reusable accelerators that just work together, and which will in turn enable a marketplace of reusable accelerators. There are three key concepts. The first is a custom interface, which abstracts a composable custom extension, which is a possibly stateful set of custom function instructions. Interfaces are immutable. Any change to the behavior of an interface defines a new interface. A CFU is a core that implements a custom interface. Each CFU may be configured with some number of that interface's state contexts. And an accelerated library is a software library that issues custom function instructions upon a custom interface. For composition, we propose two new interop interfaces. The first adds a feature called custom interface multiplexing, in which an accelerated library selects the heart's current custom interface and its state context prior to issuing custom instructions to that interface. Thus, each custom interface enjoys the full custom instruction encoding space, conflict-free. The second is the CFU logic interface, a CFU signaling standard which powers automatic composition of CPU plus CFU complexes without writing any RTL. Here's an example of a composed system comprising a set of CFU-LI compliant CPU and CFU packages, including accelerators for cryptography, compression, and a new binary neural network inference package. These are composed according to a system manifest into an accelerated system with two CPU cores going through a switch to the three different CFUs. On the right, an accelerated application with three accelerated libraries that each issue domain-specific custom instructions to their respective interfaces and their CFUs. This is all described by the system CFU map, which may be part of the device tree, that informs the runtime about which custom interfaces are configured with CFUs in the current system. This figure illustrates how the proposed new interfaces fit into the hardware-software stack. A custom interface runtime provides services such as discovery to the various accelerated libraries. A layer down, custom instruction execution using custom interface multiplexing via two new CSRs we name -ZI CFU. And then there is the CFU logic interface, the signaling standard for glueless automatic composition of CPUs and CFUs. As I mentioned, this work took several years. We kept finding new composition challenges, and we worked hard to provide simple, practical, and efficient means to address them. For example, during a thread switch, how should an operating system kernel save and restore the various stateful custom interface state contexts? Please see the specification for all of our details on these issues. In this work, composition is the paramount concern. If two accelerated libraries and their CFUs work correctly in separate systems, they must keep working correctly together. Therefore, the behavior of an extension must not change when composed with others. In this first version of the work, this is achieved by constraining the types of interfaces and CFUs we support to those whose custom instruction access only the integer registers and the interface's current state context. Each interface or CFU can have 0 or more state contexts. Stateful interfaces are typically one state context per heart. And note for version 1, custom instructions may not access other resources, such as shared memory, the program counter, CSRs, or exceptions. Custom interface multiplexing is the key enabler of composable custom extensions. It provides an inexhaustible, collision-free instruction encoding space. It uses two CSRs, MCFU selector and CFU status. A CSR write to MCFU selector acts as a prefix for the custom instructions that follow, specifying the heart's current CFU and its current state context. This figure illustrates the hardware-software interface of custom interface multiplexing in more detail. When the current instruction is a CFU reg instruction, it specifies the function ID, and the two source operands are read from the register file. In addition, the MCFU selector register provides the current CFU and state index. These are all packaged up in a CFU request, which selects the CFU, state context, function, and operands. The CFU performs the function and may read or write only the selected state context data. The CFU response includes the data result, which is written back to the register file, and a response status, which is accumulated in the CFU status register. Here's an example of a possible accelerated library programming model, in which we try and select a custom interface and issue custom instructions, if its CFU is present in the system. The library calls to the custom interface scope constructor in the runtime to look up the custom interface ID for ibitmanip. This can succeed or fail. If it succeeds, a CSR read-write configures MCFU selector to select that CFU, and then a custom pop count instruction issues. If that CFU is not configured in this system, then software falls back to a pure software version of pop count. Finally, the draft specification also proposes a hardware-hardware interop interface called the CFU logic interface that allows automatic composition of compliant CPUs and CFUs. It accommodates different levels of sophistication of the CPUs and CFUs. The CFU LI provides bindings for combinational, pipelined fixed latency, variable latency, and response reordering CFUs. It also includes pre-built switch and adapter CFUs to power glueless composition. At the right, we have an example of a CFU Level 2 pipelined variable latency signaling with request and response packets and their valid ready handshakes. In summary, these proposed new interop interfaces should allow us to achieve a marketplace of composable custom extensions and their custom function units and libraries. For more information, please review our draft proposed spec. We continue to meet to refine the spec, to socialize the proposal more broadly, to build a greater consensus, and to prototype CPU and CFU composition demos. We'll meet via the RISC-V SIG Soft CPU mailing list. Please join us. Together we can define interop interfaces so that everyone can quickly create or reuse custom extensions that work well together. Thank you.